Hello, Microprofessor friends. This is going to be, I think, really our final video about the force system that's available for the Microprofessor MPF-IP or 1+, right? And it's the force video that we are going to make. And yeah, in the last video, I demonstrated the structure of words and some internals, right? How are words represented in memory? And we learned that words are basically record-like data structures that are being created by the force word create. And then a word has a name. It also has a parameter field and a code field, right? And if we are executing a word in the interpreter or at runtime, if it's being called from within the definition of another word that, executes it within its definition, then its code field address is being executed, right? And depending on the type of word, this code field, this code which is being pointed to by the code field is doing different things. So if it's a variable, then it puts, for example, the address, the PFA parameter field address of the variable on the stack, because we need this address if we want to change the value, right, of the variable. And we learned that for executable words that run a program, basically, right, whose definitions basically consists of multiple words, then the so-called address interpreter is what's behind the code field of an executable word. And the colon compiler, as it's called, is going through the parameter field of an executable word and basically executing the addresses, namely calls to other words in the definition of the word that we are currently executing, right? And the definition is stored again in the parameter field, and the parameter field can be of arbitrary length, right? And there are different kinds of words. And words that are defining new words, right, like variable, for example, are called defining words, right? So here we are defining a word test, and it's a kind of word, it's a variable, right? And in order to, the standard semantics for a variable word is that it simply puts, if you execute it in the interpreter or at runtime, it simply puts the address of the PFA, of the parameter field, the PFA on the stack, right? And we need that address if we want to change the value of the variable. Using the exclamation mark operator like this, right? And to retrieve the value that's stored at an address, right, we use the add word. And so here we have the value, right? And for a constant, right, this is another defining word. The semantics is different, right? If we have cons as a constant, right, then rather than putting the PFA on the stack when the constant is being executed, right, we are directly getting the value, right, because you don't need the address, you're not supposed to change the value of a constant. And so that's, again, there's a little bit of a similarity to Lisp, right, as I explained, that words roughly correspond to symbols in Lisp. And I think, I mean, that's of course a conjecture, right? But I think that the inventor of force, Mr. Charles Moore, probably knew Lisp, and because there are some other similarities, right? For example, to prevent basically evaluation or execution of the word, like for example of cons, right? So now we have executed it, right? To prevent evaluation, as we would say in Lisp, you can quote it, right? And that's it's curious to see that this is exactly the same operator as in force, right? So if you use tick or quote, right, as it's called in Lisp, in front of the word or symbol, right, then you are not getting the value, you're not evaluating it, but you're getting the address basically, right, of the word rather than the value, which, and of course that's the address of the PFA, and that basically corresponds to the address of the symbol in memory, right? And so that's a similarity there again to Lisp, right? You can prevent evaluation of a symbol by using a quote, or in force you get the address and prevent execution by using the tick. So you already learned about normal colon compiler compiled words, right, which when executed have runtime semantics, right? And you learned about defining words, right, which allow us to define words that can define other words. And now a very important aspect of force is so-called compiling words, right? And these words are actually words which are executed at compile time when they are being used in the definition of other words, right? And to illustrate this, let me write a simple example here. So I'm using the colon compiler to define a word CT for compile time, right? And all it does is it prints compile, right, on the display. And then I'm terminating, terminating the definition. But rather than hitting enter, now for the crucial aspect here, crucial part, I'm typing in immediate. And this is basically a flag for this word CT, which marks it as a compiling word, right? And what a compiling word is now it behaves special at compile time, right? So first of all, now it's defined as a compiling word. And now watch what happens if we use this in another word which we are compiling now. So we are now compiling a word test, right? And as part of the definition of test, we are now using our new word CT compile time, right? And then I also want to print runtime as part of the normal execution of our test word. And I terminate the definition using semicolon, but I'm not using immediate here, right? And now watch what happens if I hit enter. So you see that before OK from the colon compiler, we also now got compile, right? And this is actually the output from our defined CT word, right? So what happened here is that when the colon compiler went through the definition of test and tried to put in the addresses, right? It saw CT and it realized that CT was marked as an immediate or as a compiling word. And that means rather than putting in the address for a runtime jump to that word, it executed that word right away as part of the compilation process, right? And then CT was executed during compile time, resulting in that output on the display, right? And this is now, of course, something very powerful because with these compiling words, you have the ability now during compilation to invoke arbitrary force code, right? And watch what happens if we now invoke test. Remember, test was defined as CT and then simple print string runtime, right? So you don't see compile on the display, right? But you only see runtime, right? So the word CT, which we put into the definition of test, right, was only relevant at compile time, right? So we say that CT only has compile time semantics with regard to test, but it does not have runtime semantics with regard to test, right? Because it simply wasn't invoked here. So the colon compiler has executed CT right away during compilation, but has not put into the definition in the parameter field of test jump a call to the code to the CFA of CT. It only has put in the code to this jump to the CFA of the print string runtime word, right? So, and we can do all kinds of funny things with that now. Okay, I just demonstrated immediate words, right? And no big deal. Those are just false words which are being executed at compile time. And I showed that, you execute it as part of a definition of another word that you are currently compiling called the compilee, right? And when the colon compiler finds it, it simply executes the false definition at compile time rather than at runtime, right? But how does that help us? How can we actually use this feature in order to extend or change the compiler, right? And this is where the similarity to Lisp macros is. So these force words, these compiling force words are called compiling force words for a reason. Namely, at compile time, they can now compute basically the definition of the compilee, which is currently being compiled, right? So you can use a compile instruction basically in order to instruct the compiler to put a certain call to the CFA of another word into the definition of the compilee, right? And that's a little bit abstract, but let's demonstrate this. It's really quite simple once you get the idea, right? So I'm defining a word a star, and all it does is it prints a star, right? And it's just a normal force word, right? We are not it's not a compiling word, right? So we can just, it has runtime semantics and it's printed the star here, right? And now suppose we want to write a macro, right, or a compiling word that does the following. When we use it at compile time, it basically expands into 3 calls to star, right? Star, star, star. So it is as if you would write star, star, star directly in the definition of the compilee, right, of the words that you are currently compiling, but you want to have that work being automated by a compiling word, and we are calling this word 3 times star, and this is going to be our compiling word. And now it's a compiling word, so it has the immediate flag set, right? So when the colon compiler finds it in the definition of the compilee that we are defining, it's being executed, right? And we can print something on the screen, as we just saw with our word CT and the output compile, right? So how do we instruct the compiler now to put in a call basically to our star routine in there, right? So our macro expansion. For this we're using compile, and then we specify what we want to compile, right? And so this is again a special word which reads from the input stream to the right? So it puts 3 calls to the word star into the definition in the parameter field of the compilee when it's being used in another word, right? So now we have our compiling word defined, and we can simply use it as follows. So we are defining a word do it, right? And as simple as that, right? So if I hit enter now, the colon compiler will find that 3 times star is a compiling word because of immediate, right? And then it will basically execute the definition of 3 times star, and that says compile star, compile star, compile star, right? And when the compiler then executes that, what compile star does is into the definition of the compilee here, of do it, it simply puts in the address to the CFA of star, right? So in the end it expands into something in the parameter field of do it, right? The definition of do it, as if we would have written star, 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 right? So remember that the PFA of a word which is executed, right, is basically interpreted by the address interpreter, right? And that calls to other words in the definition are simply calls, jumps to the CFA, right? And followed by a return then, of course. So, but this has been done at compile time now, right? It is really as if we would have written do it star, 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 print done, right? So if I execute this now, it indeed has the desired effect, right? We see our 3 stars and then done. But let us verify that the address compiler has indeed put in the definition of do it 3 calls to star, right? And that our definition do it 3 times star was really expanded into do it star, star, star. And of course I already showed you in the last video how to do this, right? Get the PFA where the definition, the addresses are stored, right? And then simply look at the content, and you see that's the first address there. It's a call to 61458, which is of course the CFA of star, right? So the first call, the first entry in the PFA is indeed a call to star. Now let's verify that the second entry in the parameter field of doIt is also a call to star, right? And we simply add 2 to the PFA to get the second entry, right? And it's the same address, the call to star again, right? And now, of course, the third entry, 4 plus content. Well, there it is, right? So indeed, the parameter field of doIt was expanded at compile time into star, 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 which is what we wanted to see. Now the compiling word 3 times star that we just defined wasn't very intelligent, so to speak, right? This was just a textual substitution basically of 3 times star by another constant string, right, which was already known at compile time, star, star, star. But more interesting compiling words, they actually perform some computation at compile time, right, and using the full power of the Force language basically. And there's again the similarity to Lisp, right? Lisp macros also have the full power of Lisp at compile time available to compute the macro expansion, right? And so how about we are writing a macro, a compiling word, unroll, right? And its purpose is to unroll basically a loop. So rather than having a loop that does something at runtime, right? Executes the loop body a number of times. If you already know the number of iterations at compile time, you can just unroll that loop and put in the calls to the loop body into the definition at compile time, right? So then you don't need conditionals and branching and loop variables and indices and things like this. So, and for this, I mean, the anticipated use cases, let me first show you this, right? So I'm imagining an unroll macro which basically specifies the number of iterations you want to, the number of calls you want to put in, right? And then basically the word that you want to execute, right? So that would basically expand into star, 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 right? And what we had previously, our 3 times star, could be implemented like this, right? And so how are we going to write such a macro, right, which does basically loop unrolling for us? And so one thing is we now need to be able to pass an argument, right, a parameter to the compiling words such that it knows basically how many calls to star does it have to put into the definition of the compilee of doIt, right? And first let me forget our old doIt, right? And okay, and we still have star defined, good. And now let me show you how we can define our unroll compiling word. So what it does is when it gets executed at compile time, it'll find the parameter field address of a word on the stack, right, like tick star, and it will use this to compute the code field address, right, from PFA to CFA. And now what we want to do is we want to use the other arguments that we have on the stack, right, namely the number of iterations or calls that we want to put into this. And basically now we want to instruct the compiler to put in that many number of calls to our CFA of that procedure, in this case star, right? And imagine first we have on the stack, first we push the number of iterations 5 on the stack and then tick star, right? So we now, in order to start the loop, we gotta get hold of our loop index, the maximum index variable, right? And if you remember the loop construct, the do loop, then first we need the upper bound index, right? And since we swapped the two topmost entries on the stack, we now have the number of iterations basically on top, right? And remember that we always have to add 1, and it starts at 1, right? So if we have 5 tick star on the stack when the compiler executes our unroll compiling word, then it first gets now the CFA of a star, right? Then it swaps the topmost stack elements, so it gets to the number of unrollings or iterations, right? Adds 1 to that, and also puts 1 then for the start index of the loop, right? And then we can just use our do loop now. And what we do is, remember we now have the CFA of our procedure, of our word on the stack, the topmost, right? And we want to duplicate this. And we use comma now in order to put this CFA basically into the definition of the compilee, right? And we are just doing this in the loop body, right? And finally, because we duplicated, we also need to drop that element from the stack, but that's the compiling word, so we put in immediate, right? All right. And now we can use our word, right? So now we have to find a way to put basically the arguments that our compiling word unroll requires on the stack, right? And this at compile time, right? So if I would put in 5 tick star into the definition like this, right? Then these values would only occur on the stack at runtime, right, when do it is executed. But obviously that's too late, because we want to now call our compiling word unroll, and that requires the arguments at compile time on the stack, right? And for this, there is one construct in force, which is basically compile time execution, right? And in the Microprofessor force, you use parentheses star, and then everything within parentheses star is being executed at compile time, right? So now at compile time, I'm putting 5 on the stack, and then I'm putting the CFA of star on the stack, and then I'm terminating this compile time execution mode, right? So those are brackets basically. And then I can just call unroll, right? And unroll is a compiling word, so it now you know, does what we just implemented, right? It turns the PFA of star into the CFA, right? Then it gets hold of the 5 by swapping it, adds 1, right? And then it starts the loop from 1 to 5, right? And it puts 5 calls to the CFA of star into the definition of the compilee, which we are currently assembling, right? Namely, do it. So, and after unroll, you know, we are just done. So if we hit enter now, then this is being executed at compile time, and we have now indeed 5 calls to star and the definition of do it, right? So let's execute do it and see that it indeed, yeah, it prints 5 stars, right? Magical. So, and of course I can use our same compiling word now. If I pass it more arguments, like 10, right? Then it will happily expand into 10 calls of to star, right? There you go. Yes, and this is of course extremely powerful. As you see at compile time, when unroll is being executed at compile time, you have the full power of force available to compute basically the definition of the word do it, right? And this is something which you only find in languages like Lisp in the macro system, right? And it's similar there, but you don't have that in C, for example. Alright guys, and finally we know enough about force and the colon compiler and compiling word so that we can attempt our first definition of a recursive version of the factorial function using direct recursion, right? And remember how that all started, and which actually got me into Force and to look at it, because I couldn't figure out how to implement my Hello World program recursive version of factorial in Force, right? It turned out I needed to learn much more about the language before I was able to do this. But let me remind you of the basic definition that I attempted and that we are going to use. So the argument that we want to compute the factorial of is on the stack, right? We duplicate that because we need the comparison now whether the argument is smaller than 2. In this case, right, remember that the smaller comparison consumes the topmost 2 entries, right? So we needed to duplicate it first in order to preserve the argument on the stack after the comparison, right? And the result of the comparison is of course now a Boolean, 1 or 0, right? 1, if it's true, then we know the argument is now 0 or 1, right? Then we want to drop the argument 0 or 1 and say, okay, the factorial is 1, right, in this case, because that's how it's defined for 0 and 1 as corner cases, right? Or actually 1 is not a corner case, but 0 is, right? Factorial of 0 is 1. Else it's 3 or greater than 2, right? Greater equal to 3. Then we want to subtract 1, and now we want to make the recursive call to compute the factorial of n minus 1, basically, right? And multiply n minus 1 with the result we got from the recursive call on the stack using times, right? And of course, as explained multiple times now, okay, we need to terminate also the then definition, the if else then in Force, right, instead of if then else. And of course, you're getting the error message that factorial fact is not defined yet. Message 0 means unknown word, right? And this is because the colon compiler only knows about fact when you terminate the definition, right? But within fact you can't use it. And for this we are now writing to tackle this problem a compiling word, and we are calling it rec for recursive call, right? And there's one word which, when executed either at runtime or at compile time, gives you the link field address of the latest word that has been created. Latest will give us the LFA of fact if we are using that compiling word rec that we are currently writing here in the definition of fact, right? So latest gives us the LFA now, the link field address of fact on the stack, and we want to execute a jump to a fact, basically, right? So we gotta compute the CFA for that word fact, right? And we can get the CFA from the LFA that is being left on the stack by latest for us by first computing the PFA, the parameter field address, and then, of course, the code field address, as we have done it multiple times by now, right? So, and with this address, we now want to instruct the compiler when it compiles the definition of fact of the compilee, where we are going to use this rec word, right, to put this address into the code, right? A jump to that address, basically. Comma basically puts in the top stack value into the parameter field in the current position, right, of the compilee. And of course, this is now an immediate word, the compiling word. Okay, and now we can indeed write our recursive definition of fact as follows. So it's the same definition as before, the only difference being that the recursive call to fact is now replaced by a call to rec, right? And rec will, of course, here's a call right now, call fact itself over the LFA, the latest LFA, PFA, CFA, and comma has put in the address now. It's going to put in the address now when I hit enter, right? And we need to terminate the if it's then. Okay, there's our definition of factorial, right? Let's check if it works. So it didn't complain. The colon compiler was able to compile it without error message 0, right? And let's test for the corner case first. Okay, factorial of 0 is 1, which is good. also works for 1, right? Does it work for 2? Now that already requires a recursive call now. Yeah. And for 3? How about 5? Well, that seems to work, right? So where's the limit? Maximum stack size. So at some point it overflows, right? Because but then at 13 or so, you know, you reach the, yeah. So I think that's the highest unsigned factorial number that we can compute. With 14, 16-bit is not enough, right? And it has overflown. Yeah, all right. So we finally have our direct recursive version of the factorial function, and that is only one way of defining it. There are others, right? And let me point out that this still does not work for indirect recursion, right? And this is what we are going to implement next. How can we address indirect recursion? So before we go and implement a version that will also work for indirect recursion, let me explain, remind you quickly what indirect recursion was, right? A classic example is basically odd and even, right? So a number is odd if, now we start with a base case, right? So 1 is odd, right? And then we want to return 1 as a result for Boolean true, right? But another base case is 0. 0 is not odd, so we want to return 0, right? Else, for any number which is not 1 or 0, we want to return the result of even of x minus 1, right? And you see that here's now a call to the even predicate, which we haven't defined yet, right? Which is problematic for force because it's again a forward reference, right? So how do we define even? Well, you might have guessed it already. Of course, we define it in terms of odd, right? But the case analysis for the base cases is now again for 1. The result is 0 because it's not even, right? For 0, the result is 1, right? And you can see that, you know, for the base case, you can achieve this by simply subtracting 1 minus the argument, basically, right? Else, if it's not 0 or 1, it's even if the number minus 1 is odd, right? So, and this is an indirect recursive version, right? Because odd calls even and even calls odd, right? So, and this is going to be problematic for our rec predicate, which we have just defined, right? Because if we start writing the definition of odd, even though we now have, you know, the ability in the definition of odd to make a call to odd, a recursive call to odd directly itself, we still at compile time do not have the reference to even, right? So that's a forward reference, and the compiler cannot put in that reference, right? So for this we need another technique, and this technique is called vectored execution. Basically what it is instead of putting in the addresses for even and odd, you put in, you instruct the colon compiler to put in addresses of variables, right, which you have already defined. So their addresses are known, and those variables are called execution vectors, right? So rather than storing values, those variables actually store the CFA, the code field address of the word that you want to call, right? So the variable that we would put in here for the call to even would contain the CFA of even, right? And at runtime, we would retrieve the value, basically the function or code pointer of that variable, right? Again, code pointer to the code of even, the CFA of even, and execute that, right? And same here for odd. And so first let me demonstrate now how to implement vectored execution, the basic version, over variables, and then we are going to extend the compiler such that we can write odd and even. So the basic idea of vector execution is very simple, right? Let me first clear this cold start the force, so we have a clean slate. So as I said, a vector, right, is basically just a variable, and rather than storing a number, it stores the CFA of a word that you want to execute at runtime, right? The point being, the address of vector is known at compile time, right? So the colon compiler can put that in, but it's getting changed basically at runtime, right? And it's only known at runtime. So only at runtime the value of the vector variable will be retrieved and executed, right? The CFA of it, right? Now that we have a vector variable, we of course also have the address, right? Because that's the default semantics. And we can execute a vector, right? And we get the PFA, the parameter field address, right? So the colon compiler can always put in this address, right? When it compiles the definitions, right? If we are using this. And now let's see what happens if we define a word for testing purposes X. And all it does is, it prints X on the display, right? Like so. And of course, I already showed you that we can execute X also basically indirectly by first getting the PFA of X, right? Tick X gives us the PFA. We transform this into the CFA by subtracting 2 basically from the address, right? This is all what CFA does. And then we can also execute it like this, right? And again, you get the same output, right? So we executed it like this. Now, so how about we now use our vector variable and store the CFA, right, of X, which we again compute like this, right? So it's on the stack now, the address that we can execute, right, which we'll call X then at runtime. And then we basically assign this using the variable and the exclamation mark set or bang operator to store that CFA of X in our vector variable, like so, right? Now what can we do with that? Okay, of course in vector now, if we retrieve the value, we actually have the CFA of X, right? 46A, 6146A, which is of course the CFA of X, right? And now we can simply, execute our vector, right? We can just get the value of vector, which is the CFA of X, and execute it. And it did it, right? As simple as that. So it's basically just a function pointer in a variable. Sorry. So let's make that a little bit nicer, right? So how about we define a word for this and we call it exec vector, exec v. And all it does is it expects the PFA of the variable on the stack, right? It retrieves its value, then the CFA, and then executes it. So, and now we have the CFA computation at runtime, right? So we then can assign our vector a little bit nicer without having to put the CFA in here when we do the assignment to the vector variable, right? And so vector doesn't contain the CFA of X now, but the PFA, right? And we can use our newly defined exec v to execute our vector, right? So we can do vector exec v, and X is getting executed. Yeah, and that's now really the key to vector execution, right? Because we can now easily change, the vector basically. See if we also have a definition y, which unsurprisingly prints y on the screen, right? And let's define a test word which is now using our vector and our new execute vector, right, to make the call instead of putting, you know, the call to x or y in there directly, we now have a variable, right? A pointer which can be changed at runtime without having to change the definition of test. And if we execute test, then, you know, x will be executed. But, and that's the point now, without changing the definition of test, I can now simply change my vector, right? I can say, you know, vector, instead of pointing to x and execute x at runtime, I rather want to point to y now and execute over the vector. I want to execute y at runtime, right? So, and without having changed test, it executed y now, right? So this is vector execution, and we are going to use this to implement the indirect version of recursion. Alright, but before using vector execution to implement the mutual or indirect recursive version of odd even, I want to take the advantage to one more time demonstrate compile time execution of force, right? Again, using recursive version of factorial. And now that we know what vector execution is, rather than using latest and PFA, CFA, comma, right, in a compiling word, we can also do this without a compiling word. And I used that construct before here, parentheses star, right? Now everything within this block in these parents is being executed at compile time, right? And there's a word here, which always returns on top of the stack the current parameter field address in the dictionary, right, of the compilee, right? So the latest dictionary entry that can be populated, the address of that, right? Since we are compiling fact here, this is going to be at compile time now the PFA of fact, right? And basically the first field, the address of the first field in the parameter field of fact, right, where the colon compiler puts in the definition, compiles in the addresses. And again, we are now getting the CFA, right, of fact, and we basically store this now at compile time in our vector, right, using the assignment operator. So at compile time, without using a compiling word, but using compile time execution, right, using this block here, we achieve the same effect as before, right? And now the definition is of course the same. First we, let's do a different definition this time, right? But first we duplicate the argument on the stack, right? And this time we are checking if it's greater than 1. And now if it's greater than 1, right, then we are doing the recursive call. We just swapped the clauses around a little bit, right? And we subtract 1 from the argument. Now comes the recursive call, but rather than using the compiling word rec, right, we are now again using compile time execution. And all what we do is, you know, at compile time, we are now getting the value of vector, which is of course now the PFA of fact, right? And actually the CFA of fact, because this is how we assigned it, right? And we're getting the value here, and then we instruct the compiler now to consider this, what's on the stack, compile this into a literal, right? What that means is that the value on the stack, which is being put into the code now, is it's producing code to actually push that literal on the stack, right? And then at runtime, you know, this value that we compiled into the definition using literal can be executed, right? Because it will also be on the stack now at runtime when we execute fact. And then, of course, now the result of the recursive call to fact now over the vector is on the stack, and we multiply it with n-1. Okay, so let's see if it works. And it does. So you see that this has achieved the same effect basically as the compiling word. Right? We can also use comma again. So let me define fact2, which is slightly different, right? Again, we are using vector execution to store the address of the CFA of fact over here in our vector, right? So that we have it available at compile time. And then it's the same definition as before, but rather than using literal now, first let's retrieve the address from the vector, right? The CFA of fact. Rather than using literal and execute, right? We now use comma at compile time, and we used that before, and as explained, comma just inserts into the parameter field of the compilee what's currently on the stack. So it's basically the value of the vector, which is the CFA of fact, right? And so that's the nicer way to do it. Fact2 also works. All right. Well, but now let's again use a compiling word to make our recursive definition of factorial that we just implemented a little bit nicer to read, right? And also it would be nice, since we are now using these vector variables, right, to actually have a defining word that allows us to create, you know, labels basically, or variable vectors just for that purpose, right? And how about we just, you know, write a defining word label, and basically it's just the very same thing that variable does, but it's just nicer to look at in the code, right? If you can use label, because it makes explicit what, you know, the variable word that you are using is supposed to do, what's its purpose is, right? It's not just a general purpose variable, but it's storing the address, the CFA of another word, which is meant to be executed at runtime. So, and a defining word, of course, has this is using create, right? So we are using create now to create the label, right? And we are allocating two spots in the parameter field, and then at runtime there is no special semantics, right? The runtime semantics of this label that we have defined with our defining word label, we just put its PFA on the stack, right? So we can now use label to create our, you know, our vectors. How about we have a label Q, right? Or this is basically the same as variable vector we used before, right? But now we can declare a number of labels, and instead of using that complicated compile time computation to determine the reference and get the value from the vector and execute it, right? We define a compiling word def now, right? And it's doing the same thing basically. It stores basically the CFA of the currently compiled word into the variable, right, into our label that we also have on the stack, right? So we now have the first we expect the label, the variable on the stack, right? It's PFA, and then we have the CFA of the word on the stack, right? And now we have to swap these, right, in order to use the assignment word exclamation mark, right, to basically change the vector address of the variable, right, of our label, and that's a compiling word, so we are putting an immediate. So, and then this is being used in order to establish to set the label address, right, in the code, right? And now for the recursive call, we are defining another compiling word, which simply retrieves the value, right, of the label of the variable, and puts this address, right, and it's already the CFA which is stored there, into the code, right, that is being currently compiled using comma, and of course it's a compiling word. So we are going to use this now as follows, right? Note that I did a cold start, so the previous definitions are gone. So first we are now putting the the PFA of our variable, of our vector, of our label Q on the stack at compile time, right? So the compiling word def now finds that address on the stack, and it uses it basically to store the CFA of here, which is again, of course, the CFA of fact, which we are currently defining, into that variable, into that label Q, right? And at compile time, and then we can just continue with our normal definition of a factorial function, same as before, right? And now for the recursive call, again, we need to make sure that we have at compile time the the variable on the stack, right? The PFA of Q of the label, right? And now we are using our compiling word rec, which puts in the recursive call, right? And let's see if this works. It does. And I mean, that's much nicer, right, than what we did before. Because now we have the ability to define labels using def and just put in jumps to these labels using rec, right? But, wait a minute. If we have now a forward reference, right, then we cannot determine the value of Q at compile time. So that wouldn't work for odd and even, right? That works for direct recursion, because the address of Q, remember we put it in like this, right? The address of Q has to be known at actually the value of Q, right, which is the address of fact, the CFA of fact, has to be known at compile time, right? But that's not the case for mutual or indirect recursion like odd and even. So that won't work for mutual recursion, but it's a first step towards making a nice compiler extension, right? Having your own syntax and compiling words and defining words and labels and a little bit of compile time execution. And so let's see how we can change this to make it work for odd and even. So now it's time for the final exercise. We are now finally defining our mutual indirect recursive version of odd and even, right? Here's the definition again. And as just explained, we have a problem now, because even though we have vectored execution and compiling words, we still have a problem now, because when we are compiling the definition of odd, right, the compiler does not know the CFA of even yet, so he cannot put in the address, the call to even at compile time, right? Rather, we can only know the address, the CFA at runtime, because even is going to be defined after odd, right? So what we used for factorial, right, where we would have rec, our compiling word rec, put in the address, the CFA of fact at compile time, right, does not work here. But it's a small change only, right? So all we got to do is basically change rec to an ordinary false word, which at runtime then fetches the vector address and executes it, right? So let's see how we can do that. And I did a cold start, right? So we got to put in our definition again. We start by creating label again, which is, as explained various couple of times by now, is just the same as variable, but gives us a nicer syntax, right? So because it makes the intended use of the word of the variable explicit, right? And so we can then define two labels, one for even and one for odd, our vector variables, EL and OL, right? And again, we need now def in order to establish the vector, right? And it's a compiling word. The vector is being assigned at compile time when the compiler goes through the definition, right? And now we have to change rec. This can no longer be a compiling word, but instead it's just fetching the address, the vector address, right, from the variable, from the PFA, which is on the stack when it's being executed at runtime, and then we execute that vector stored there. Good. And now we can finally define odd and even. So at compile time, we are now making sure that the label for odd is on the stack. So def can use that label to establish the CFA reference to odd, right? CFA of odd. Over here, CFA swap and then set, right? As just shown in the definition of def, right? The compiling word def. And now we have to make the comparison. So if we have 0 or 1, right? So if the argument is smaller than 2, then in that case we have 0 or 1, right? And that is already the answer, right, to the base case basically. So the if clause doesn't have to do anything, but for the else clause, of course, right, we have to now subtract 1 and call even recursively, right, using even label, and do our call to rec over the vector. Okay, and for odd it's going, sorry, this was odd. For even it's going to be the same thing, right? At compile time we are now putting the label on the stack so that def has it available, right, to establish the vector address, store it in the variable. And again we have to duplicate in order to make the comparison. And remember, for 0 and 1 now we have to swap it, because 0 is even, right, so the Boolean result should be 1, and 1 is odd, so it's not even, right, so the Boolean result should be 0. Then in order to do this we just put 1 on the stack, then we swap the arguments, and then we basically negate the value, so to get the right Boolean value, right? And in the else case, of course, we got to do the exact same thing as we did for odd, but this time we have to establish the jump to the odd label, right? And then we terminate the definition. So let's see if that actually works. Is 10 even? There you go. Is 11 odd? Yes. Is 11 even? No. So, and does that also work for the base cases? So how about 0? Is 0 even? Yes. Is 0 odd? No. Is 1 even? No. Is 1 odd? Yes. So, that actually worked. Alright guys, I think we really reached the end of our force exploration on the Microprofessor by now. Maybe I do one more video, not sure yet, but for now I think that's really it. And yeah, I hope you enjoyed this exploration into the force system on the Microprofessor MPF-1+. So we explored and understood a more than 50-year-old language on a 40-year-old piece of hardware, right? The Microprofessor, well, almost 40 years old by now. And if you want to learn more about force, right, then I recommend you start with this book, Starting Force by Leo Brody. This is what got me started into force, and I actually got this book for free from a gentleman who had an exhibit at the Vintage Computer Festival West in Mountain View last year in 2021, right, which is here next door, Mountain View. I live in Palo Alto. And he had a Jupiter Ace force computer, right, and some other, force systems up for demonstration there. And he also had a whole box of, these books, right, which are, basically new. A new old stalker. I don't know how he got a whole box of those, right? But he was giving them away for free, and I was lucky to get one from him. So thank you very much for this. And it really made a difference in my force learning, right? Because with this book, last summer I just started to thumb through it, and I found it very appealing with its illustrations, etc. And at first I thought it was a bit too shallow, right? But then on page 220, when it starts about how the system works under the hood, I realize that that is really deep, right, and you know, very interesting, right, and it took me a while to understand all this, and some things I didn't understand at all reading it, so that was a nice challenge. So I mean, the concepts, etc., all that applies to the microprocessor force, but there are also big differences, right? So for example, vector executions, as we just discussed it, right, if you look into this book, then I mean, setting the vector, right, to the pointer works just like that, but you know that we need the CFA actually in order to execute the pointer, right? So this will immediately crash on the microprocessor, right? So there are some differences to what's being described here, right? And also, you know, the syntax of standard force is different, right? So I made a lot of notes in this book basically, but it's a great book, and so I think it discusses a dialect basically of force as its main dialect here, which is Polyforce, right? I think this was the product of this company Force Inc., of which the author Leo Brody was the president or CEO or what have you, or founder, right, or all of it. And so in the appendix it discusses basically the differences to the Force 79 standard, right? And some of the standards apply to TIC, for example, but others apply to, you know, CFA and vector execution and what we just discussed. But a great book, right? And drawback is it doesn't discuss recursion, right? But it gives you all the under the hood picture, right? And the structure of a dictionary entry, things like this, all what we discussed, right? With code pointer and parameter field and LFA, structure of a colon definition, how the colon compiler works. So very, very nice illustrations. That's a great book. I highly recommend you read this, right, if you really want to understand what's going on. And I started learning force backwards basically, right, because I said, okay, I have a PhD in computer science. I should just be able to, you know, put in my standard hello world example, which is, as I said, the recursive definition of the factorial function, right? And I couldn't get it to work, right? And then I Googled basically for how to do recursive definitions in force, and I found a PDF version of this book online as a hit to my query. Thinking Force from the same author that wrote Starting Force, right, Leo Brody. And this is the you know, the next level force learning book. So and this is even deeper, right? So, and this gives a solution to recursive definitions, right? And in order to do recursion direct or indirect, he proposes to use constructs and words called DOER and make, right? And those are compiling words and some not, right? But it also then allows you to do indirect recursion like so, right? DOER B, and then with an A you can call B, and then, you know, this is how you would. And I must say, I find that a little bit confusing to do the odd-even example like this, right? And I had a hard time understanding how DOER and make works, right? So the implementation of DOER and make for various force dialects is given in the appendix B, right? And I think it took me about really a full month until I fully understood how DOER and make basically works, right? Because you basically need to understand all of it, what we covered in my videos, right? The structure of words, vector executions, how the compiler works, and all that, right? Compiling definitions, and so the definitions of DOER and make that are then being listed in the book, right, for various dialects of force, Force 83, Force 83 lab, and Fig Force, right, and 79 standard MVP force. None of these work on the microprocessor, right? So the microprocessor is somewhere in between those two, right? And you see the address arithmetics which you need to do in order to go from PFA to CFA and what have you, right? that is apparently the structure of words, how things are arranged, whether the CFA is -2 or +2 of the LF, the link field, or what have you. Those things can be different in different fors. So that took me quite a bit of time to figure out basically how to write DOER and make in the for the Microprofessor, right? And by now I have a working version of DOER and make for the Microprofessor. So maybe I do one more video where I share this version of DOER and make that I, based on my studies and based on this here, I created for the Microprofessor, and that will then really be the final version of our fourth series of videos. So yeah, okay guys, but I mean, so much for now, and yeah, maybe one more video. Stay tuned, and until next time, right? Bye.